Right, continuing where we left off, we're getting into section 6.6, chapter 6, section 6.6, and here we're talking about Lewis structures for molecules. So we looked at Lewis structures for elements, where we looked at the Lewis dot structures when we looked at elements. Now what we're going to do is use the same Lewis dot structures, but then we'll use the Lewis dot structures of the elements and make compounds applying the octet rule. All right. So carbon has got 4 dots. It's in group 4 valence electrons. Hydrogen has got 1 dot because it's in group 1 valence electron. So in order for carbon to get an octet, it has to combine with 4 hydrogens, and now it has 2, 4, 6, 8. So by sharing of those 8 electrons, 4 from carbon and 1 each from each hydrogen, hydrogen doesn't need an octet. It has only a 1s level, so it only needs a duet, like helium. It's a duet. So it's hydrogen is satisfied, and so is carbon, because now it has an octet. Similarly, here in nitrogen, nitrogen is in group 5, so it has 5 dots. All right, 2 of them are already paired, and then 3 are available for bonding. So it combines with 3 hydrogens, and now it has an octet. All the hydrogens are satisfied with their duets. In water, again, oxygen is in group 6, so it has 2 available electrons for bonding, and so again it combines with 2 hydrogens. All right. So this is how the Lewis structures for molecular compounds are represented. Okay. So the simplest molecule is the H2. All right. Now there are the gases that exist as diatomic molecules, but because in their natural state, that's how they exist, they are considered to be elements. So hydrogen is one of them. All right. So in a hydrogen molecule, each hydrogen brings 1 electron and they share it between them, and they achieve the nearest noble gas, which is helium. All right. So by sharing those 2 electrons between them, they have their first shell, that 1s2, that is complete, and now they've achieved stability. All right. So now when this happens, remember, in the nucleus of the hydrogen there is a proton. All right. So as they're coming now here, when they're further away, there's not much of an attraction. Now as they come closer, the proton of this hydrogen is influencing that electron of the other hydrogen, and there's a pull pulling it towards it. All right. Same thing happens. The proton of this hydrogen is exerting an attractive force on this electron of the other hydrogen. All right. So there is a pull drawing them together. But at some point, if they get way too close, the repulsions between the electrons, because unlike charges attract and the like charges repel, becomes too much. So there is a certain comfortable distance at which they can come closer, and that way the 2 electrons can be shared equally between the 2 hydrogen atoms when their orbitals are overlapping, like you see here. All right. If you look at the energy and the distance between those nuclei of those 2 hydrogen atoms, you will see that when they are far, that energy is really high. All right. There is a lot of repulsions, etc., happening. All right. Now as they're getting closer, all right, that the unlike charges attractions are overcoming those repulsions and bringing them, and that's why you can see the energy is decreasing. By the time they are bonded, that is at the lowest energy. All right. As you can see here, energy is increasing this way. All right. So they are the lowest energy. So bonding is very stabilizing by themselves. the hydrogen atoms are not very stable, but when they bond and they form the hydrogen molecule, you can see that they are stabilized because they are at their lowest energy. Okay. So in a molecule, if you look at the Lewis structure, the bonds are represented like so, either by the dots or by lines like here. So the lines, each line indicates two bonding electrons, all right? So one line is equal to two electrons, all right? So there are three bonds in ammonia. This is ammonia. And then those electrons of the nitrogen that don't take part in bonding are called as lone pairs or non-bonding electrons. So two fluorines coming together, they come together. Fluorine is in group 7, so it has 7 electrons, and so it's one short of an octet. So it comes together with another fluorine, a bond is formed. This is the bonding pair, though there are 3 lone pairs on each fluorine, all right? And you can represent that bond with a line. And so this is F2, all right? So again, fluorine, like hydrogen, is an element. It's a diatomic element, all right? So it exists in nature as a gas as F2, okay? All right, so there are 7 elements that exist as diatomic molecules. You must learn this, all right? If you have to find a way to memorize, then do so. This will not be provided for you in an exam, all right? So those 7 are hydrogen, nitrogen, oxygen, and the halogens, fluorine, chlorine, bromine, iodine, all right? So these are the 7 diatomic molecules, but they are considered to be elements and not compounds, okay? All right, so if you look at bonding patterns, okay, it's easy to see by the number of dots, okay? Hydrogen has 1 dot, 1 valence electron, so it forms 1 bond. Boron has got 3 dots, 3 bonding electrons, and it forms 3 bonds. It is an exception, as is hydrogen, to the octet rule, all right? So boron only forms 3 bonds, and each bond means 2 electrons. So that's a total of 6 electrons, so it's too short of an octet in its compounds, all right? Carbon, silicon is in group 4, so they have 4 dots, 4 bonding electrons, so they are able to form 4 bonds. Again, how do you determine the number of bonds formed? 8 minus the group number, all right? 8 minus 4, so 4 bonds. 8 minus 5, so 3 bonds. 8 minus 6, 2 bonds. 8 minus 7, 1 bond. All right, so you have carbon with the 4 bonding available electrons for bonding, hydrogen with 1 available electron for bonding. They come together, 4 hydrogens and 1 carbon, and you get CH4 or methane. Okay, we already discussed the ammonia and water, all right? Ammonia forms 3 bonds, 1 lone pair, and water forms 2 bonds and 2 lone pairs. All right, so how do you determine the electron dot formulas or the Lewis structures of compounds, all right? First, you have to determine what are these arrangements of atoms in these compounds, which is the central atom, which are the side or the surrounding atoms, what are the total number of electrons, and then make sure that all of the atoms are attached by a line, a bonded pair of electrons, all right? Once you form the bonds, you have to determine how many remaining electrons are there. Do you need to make multiple covalent bonds to complete the octets? Is all the atoms satisfied in terms of octets or duets for hydrogen, all right? So those are some of the rules to follow. Okay, so it says draw the Lewis structure for PCl3. Okay, phosphorus has 5 available electrons for bonding, but 2 are lone pairs. All right, two are belong to the non-bonding or lone pair. So 3 available valence electrons. Each chlorine can also bring 1 available electron. So PCl3, you start out by writing the first element is always the central atom. All right, so here phosphorus is the central atom and you have the 3 chlorines surrounding it. Then what you do is determine how many electrons are available for bonding. All right, 1 phosphorus, 5 electrons, 3 of the chlorines, 3 times 7, so 21 electrons. So number of valence electrons is the group number. Phosphorus is in group 5, so 5 electrons. Chlorine is in group 7, so 7 electrons. So total of 26 electrons to be distributed between the 4 of them. All right. So you'll first attach the surrounding atoms by lines. Each line equals 2 electrons. So you've taken care of 2, 4, and 6. All right. So what you'll do is once you've taken care of those 6 electrons, you will subtract it out of the 26. So that leaves you with 20 electrons. Then you want to make sure that all the chlorines have got octets. All right. So you'll put 2, 4, and 6 around each chlorine. All right, so 6 times 3, that's 18. All right, then you come back here. You had already used up 6 for making the bonds between phosphorus and chlorine. Then you used up so that left you with 20. So once you used up 18 more electrons to form the octets for chlorines, that left you with 2 electrons. So any remainder of electrons after you make octets for the side atoms, the surrounding atoms, go on to the central atom. So phosphorus ends up getting those 2 electrons. So all are now happy. You have 2, 4, 6, 8 for each chlorine, 2, 4, 6, 8 for each chlorine, and then phosphorus is 2, 4, 6, and 8. So sometimes there's not enough electrons to complete the octets, then you have to form either double covalent bonds or triple covalent bonds depending on what that situation is. All right. So hydrogen just requires 2 electrons and it'll be satisfied. Now there are certain non-metals like phosphorus, sulfur, and in some cases chlorine and bromine. They are exceptions to the octet rule. All right, hydrogen is an exception, boron is an exception, beryllium is also an exception. Beryllium only requires 2 bonds, so it's 4 short of an octet. Boron is 2 short of an octet because it only requires 3 bonds. All right, so here in sulfur in SF6, like you see here, so it has got 2, 4, 6, 8, 10, 12. All right, so way more electrons around it than an octet, the required octet. All right. Phosphorus also forms a PCl5 where it violates the octet rule. All right, we'll stop here and continue this in the next video.